To this video lesson on the ideal gas law. In our last lesson, we explored quantitative relationships between pressure, volume, and temperature. And in this lesson, we are going to fold in those quantitative relationships and how they also interrelate with the moles of a gas, which has to do with Avogadro, which is, you might recognize his portrait here. So in the combined gas law, we saw the following mathematical relationship. We saw that P times V divided by T was equal to a constant. And we used this to create a mathematical equation that said the pressure, the initial pressure times the initial volume divided by the initial temperature was going to be equal to the new pressure times the new volume divided by the new temperature, right? So that was what we called the combined gas law. We use this to predict changes in either pressure, volume, or temperature. But we didn't factor in the other variable that can also affect a gas's measurable quantities, and that is the number of particles, otherwise known as moles. Right? So what we now are going to see is P times V divided by T, but we're also going to use N as the variable that stands for the number of particles, N standing for number of particles. Because the number of particles is directly related to the volume and therefore the pressure, the mathematical relationship is that pressure or volume or both are divided by the number of moles, right? And so this is going to be equal to some constant, right? So just like it was equal to a constant up here, now we're just factoring in that the number of moles is also going to play a part in this. So we can figure out the numeric value of this constant based on standard conditions, as if you had 1 mole of a gas at 1 atmosphere, 273 Kelvin, and 22.4 liters. So if we plug in for the pressure 1.00 atmospheres, and if we plug in for the volume 22.4 liters, right, because we know that 1 mole of any gas at standard temperature and pressure is 22.4 liters, and we then divide that by 1 mole, and then we divide that by the temperature of 273 Kelvin. Now what's interesting here is that none of these units are going to cancel. So we are going to have a very odd unit. It is going to be atmospheres times liters divided by moles times Kelvin. That whole unit is the unit. All right. So now let's figure out what the value of this constant actually is. All right, and so we're going to put it into the calculator. So of course 1 times 22.4 divided by 1 divided by 273. And we get the value 0. We're going to go to 3 significant figures here, 0.821. So this value, this constant, is called the universal gas constant. And for some reason that I am not entirely sure how it came to be, we use the letter R for this constant. So when we need the value of R, this universal gas constant, it is 0.0821 atmospheres times liters over moles times Kelvin. And yes, this unit contains all of these units, which is for sure a hassle to write out, but it's brilliant and it is perfect because these units are will be able to cancel out the other units in the equation that we're going to introduce to you in this moment. Okay, so we now know, going back up to this equation here, P times V divided by N and T is equal to a constant, which we are now calling R. Okay, so PV over NT is equal to R. But we're going to rearrange that into the familiar form of the ideal gas law, and it is PV equals nRT. This is what we call the ideal gas law. And it is not on the reference tables, but it is fairly simple to remember. So PV equals nRT, or as many chemistry teachers like to refer to it as PivNert. PivNert. Yeah, it's silly because that's how it would be. That's how it would sound phonetically. But all right, when to use this equation? We talked about when you use the combined gas law. Going back up to this one. The combined gas law, you use this when the conditions are changing, right? Because we have initial conditions and we have new conditions. So this is the equation when you are reading a problem and the pressure changes or the volume changes or the temperature changes. Ideal gas law doesn't really accommodate in its form that it's in now 4 changes. This is just a single pressure, a single volume, a single quantity of moles, and a single temperature. So you use this equation when the conditions are not changing, or when you are given the number of moles or the number of grams of a gas. Okay. All right, so a note about the units. Sorry, let me adjust the camera there. A note about the units. Pressure units must, when you plug in for P, this unit must be atmospheres, because it's got to cancel with the atmospheres in the universal gas constant. Volume, by the same logic, needs to be in liters. The temperature units, as you might expect, must be in Kelvin. And the mole units must be mole. Okay. Now, sometimes you're going to be given a mass, right? So if given a mass, you must convert that to moles first. Okay, let's take a look at how we use this equation, what types of problems, and let's talk about best practices, how to convey your algebraic work so that you are communicating how you justify your answer. Okay. All right, so we've got the universal gas law, PV equals nRT. I've written down here what the universal gas constant is. You will not have to memorize that. This will be provided to you for a test. So note about best practices. Okay, let's take a look at best practices while we try a problem. Okay, at what temperature would 2.10 moles of nitrogen gas have a pressure of 1.25 atmospheres and in a 25-liter tank? So once again, the suggestion is to make some sort of table to organize your data, and also to rearrange the equation for the variable of interest, and then go ahead and substitute and solve, or plug and chug. So taking a look at this, at what temperature would 2.10 moles, so we're given our moles right there as N, what temperature would 2.10 moles of nitrogen gas have a pressure of 1.25 atmospheres and in a 25.0 liter tank? So we are asked to find the temperature, so that is our X. Okay, so PV equals nRT. We are trying to solve for temperature. So rearranging this equation, temperature is equal to PV over nR. All right, so now it's just ready to substitute in our numbers. Our pressure is 1.25 atmospheres. The volume is 25.0 liters. Number of moles, 2.10 moles. And then R, 0.0821 atmospheres liters over moles Kelvin. Okay, so let's take a look at units canceling. Atmospheres are going to cancel with atmospheres. Liters are going to cancel with liters. Moles are going to cancel with moles. The only unit left over is Kelvin, and because it is in the denominator of the denominator, once you simplify, this Kelvin is the unit left over in the numerator. So now it's just a matter of putting these numbers into your calculator. Right, we've got 1.25 times 25 divided by 2.1 divided by 0.0821. Okay, and looks like we have 3 sig figs everywhere, so 181 Kelvin is the final temperature, or is the temperature. All right, let's take a look at the second problem that we have to try here. What volume is occupied by 5.03 grams of O2 at 28 degrees Celsius and a pressure of 0.998 atmospheres? What volume is occupied? So volume is our X. We've got 5.03 grams, but that is not moles. So we have to convert. So this is grams of oxygen to 1 mole. 1 mole of oxygen will be 32.0 grams. And so we do the math here, 5.03 divided by 32, and we get 0.157 moles. The temperature was given to us at 28 degrees Celsius. We have to add 273. 28 plus 273 is 301 Kelvin. And the pressure of 0.998 atmospheres, we can keep that because that's the unit that works for the universal gas constant. So PV equals nRT. We're trying to solve for volume, so I've got to divide both sides by P. V equals nRT over P. Okay, time to substitute. Volume is equal to the number of moles at 0.157 moles. The universal gas constant, 0.0821 atmospheres, liters over moles Kelvin, times the temperature of 301 Kelvin. Kind of running out of room there. Divided by the pressure of 0.998 atmospheres. All right, let's take a look. Units canceling, I've got moles and moles canceling. I've got atmospheres and atmospheres canceling, and I've got Kelvin and Kelvin canceling, leaving me with liters. And the math now becomes 0.157 times 0.0821 times 301 divided by 0.998. And we get, looks like we are looking for 3 significant figures, so 3.89 liters. All right, there you have it. The ideal gas law, a couple of practice problems. I believe there are some problems to try in the problem set. So let's try those, and I will see you back in the classroom.